So I'll be telling you about these two papers that actually we took about 3 years to finish in collaboration with Tristan Smith and Karen Mingarelli on pulsar timing array, and specifically on building a Fisher formalism for pulsar timing arrays. Okay, so we've come a long way since Galileo's first telescope. In some ways, we've come a long way. In particular, we now have instruments that can observe something like 20 plus orders of magnitude of frequency across the electromagnetic spectrum. And with these instruments, you can probe a vastly different range of physical phenomena. I will give a brief overview and motivation from the point of view of what we have learned from the CMB, being myself a cosmologist, in the far left here on the radio wavelengths. So the CMB success story, as you probably all know, it's kind of weird to talk to you guys and no one is here, but anyway. So in 65, Penzias and Wilson measure, and here there should be something that says 3 Kelvin. So I don't know if we can remove this thing here. No. Why is it on my screen? It's not on my screen. Okay, all right. So I just have to remember what's on my slides. Okay, so it was predicted a while ago that there would be something like a few degree Kelvin radiation from the Big Bang, the cosmic microwave background. It was detected by Penzias and Wilson in 65, interpreted as the CMB by Dickey, Peebles, Rowland, Wilkinson. And this one single number already allowed us to have a good understanding of the thermal history of the universe with that one single number. Now, this radiation was predicted to be in thermal equilibrium, and indeed, it took about 25 years to confirm this, almost simultaneously by the Kobe-Firas team and by the Cobra team in 1990. And they measured that the cosmic microwave background indeed has a frequency spectrum which is consistent with the blackbody spectrum. At the time, it was within 1%, and now we know that it's consistent within 0.01%. And from this, what we have learned from this, many numbers, we have been able to set some stringent bounds on the energy injection or extraction in the early universe, starting a few months after the Big Bang. After that, shortly after, the same instrument, the different instrument on the same satellite, Kobe-DMR, made the first full sky map of the temperature variations of the CMB, and this propelled cosmology into the modern era. The CMB temperature maps were measured to better angular resolution and sensitivity by WMAP and then Planck, and not only the temperature, but also the polarization maps. And from this, we have now these exquisitely precise measurements of the energy budget of the universe, as well as characterization of its initial conditions. For example, we know very precisely how much dark matter there is, even though we still don't know what it is made of. So we are now in the very early days of gravitational wave astronomy. The first telescope equivalent would be LIGO. Just like for electromagnetic waves, there's a broad spectrum of gravitational waves as well as physical processes that can generate them. So LIGO is the only instrument that has actually detected something directly so far in the kilohertz or so frequencies. We expect LISA eventually to look for massive binaries and extreme mass ratio in spirals in the millihertz frequency regimes. And what the focus of this talk is going to be about is pulsar timing arrays, which are an ongoing, multiple arrays which are ongoing and are trying to measure gravitational waves with frequencies of a few nanohertz, and this nanohertz correspond to a period of something like 10 years. The 10 years comes from the time span of the experiment themselves. And so they can measure, well, I'll get back to this, they can measure not only in principle what is called continuous waves, i.e. Gravitational waves from individual supermassive black hole binaries, but also perhaps a stochastic gravitational wave background. And this is my own personal prediction for what the stochastic gravitational wave background should look like, and it's going to take many years before it's disproven. So what are the sources of nanohertz gravitational waves? So first and foremost, the most standard source would be in spiraling supermassive black hole binaries. if you just use Kepler's laws and use the fact that the frequency of gravitational waves for a circular orbit is twice the orbital frequency, you get that it would be something like 3 nanohertz, so 1/10 years. For a mass, a total mass of 10 to the 8 solar masses, for a separation of 1% of a parsec, and for a binary at redshift 1. Okay, so of course, to see this emission, you would require these binaries to overcome the so-called final parsec problem. So if you have many supermassive black hole binaries on circular orbits, you would not necessarily be able to detect any one of them alone, but they would together lead to a stochastic gravitational wave background with some characteristic strain. And this you can show by using just the quadrupole formula for gravitational waves, etc. The gravitational wave amplitude would scale as frequency to the -2/3. And the coefficient here would basically depend on the typical mass of the supermassive black hole binaries and on the abundance of remnants. So that's the first source, the most standard source that we expect. Then what you could also get is primordial gravitational waves, either what I would call truly primordial, if inflation generated some gravitational waves at the appropriate frequencies, or sourced, for example, at second order by scalar perturbations. And here the frequency of gravitational waves would be a nanohertz if we're talking about primordial perturbations with a wavelength, a comoving wavelength of about 1 parsec. Okay, nanohertz is about a year orbit and a year period, and so parsec wavelengths. So you can, in principle, also probe the initial conditions in the universe at extremely small scales through pulsar timing array. Lastly, some exotica, for example, cosmic strings, which I know nothing about, but I was able to Google it and find some cute simulation here. So those also could generate some gravitational waves if they cross, etc., etc. So what is the current status of pulsar timing arrays? So pulsar timing arrays are still in the pre-Penzias and Wilson era. They're still trying to measure one single number, this 3 Kelvin that was measured by Penzias and Wilson. And so far, they've only been able to set constraints on it. So assuming that you have a perfectly isotropic gravitational wave background, assuming a specific frequency dependence, just like when we say 3 Kelvin, we're implicitly assuming a black body radiation. Then one can set a limit on the characteristic amplitude of the gravitational wave strain as a function, say, of this power law here. And this is a plot showing these limits from the nanograph collaboration, not the latest release, but from the 11-year data analysis. So typically these amplitudes, so for alpha of 2/3, typically the upper limits that one gets are something like a couple times 10⁻15 in the characteristic strain. So this is the status, as I said, is still the pre-Penzias and Wilson era. But looking ahead, the next step, hopefully, if one actually does detect this one number, would be to look for what is the frequency spectrum of the gravitational wave background. In fact, you can already put some limits on a frequency by frequency bin, but you don't measure the spectrum, but you can play the game of putting some limits. What you will learn here is something about, so this one single number would tell you something about the overall typical masses and typical abundances of the supermassive black hole binaries. But if you measure a spectrum, you would learn something about how eccentric they are and what other processes can damp their separations, for example, dynamical friction and things like this. So we would learn some more about the astrophysics. Looking ahead, and this is going to be also the main focus of this talk, anisotropies in the gravitational wave background. So if, again, the main source of gravitational waves at these nanohertz frequencies, if it's the supermassive black hole binaries, because you have a finite number of them, you do expect, out of discreteness effects, that you would get some level of anisotropies in the gravitational wave background. Looking even further ahead, I don't know how many years ahead or decades ahead, but one could also search for polarization in the gravitational wave background. Here I'm plotting the Planck polarization map. For electromagnetic waves, you represent polarization by little headless arrows, but for gravitational waves, I'll let you think about it a little bit. you should represent it by little headless crosses. And I'll get back to this in a moment. So, given all these, again, we're in the very early stages, but nothing prevents us as theorists from, first of all, thinking of what physics one might learn from observing these different properties of the gravitational wave background. But the focus of this talk is more from the instrument point of view, is what can we actually measure in the first place? What can pulsar timing arrays actually measure? What kind of information they have access to? And this is a question that you can, in principle, answer by using the tools which are currently available to the PTA experts, running Monte Carlo, Markov chains, et cetera, et cetera. However, those tools are somewhat, first of all, difficult to access if you're not an expert, and they are extremely time-consuming. And also, it's very good to have some other approach to have a deeper understanding of what's going on. So this is why motivated us to build a Fisher formalism. So there's no such a thing as a Fisher formalism that is widely used for pulsar timing arrays. So for the people in this room, I'm sure you all know what a Fisher formalism is. My simple description of it is that it's the theorist's reduction of the data analysis process. Just the theorist's simplification of the data analysis process, hopefully keeping the essentials. So why do we want a Fisher formalism? So to detect a gravitational wave background, you can only do this by using pulsar cross correlations. You cannot just use individual pulsar autocorrelations. You need pulsar cross correlations. Already with current pulsar timing arrays, they use tens of pulsars corresponding to hundreds of almost 1,000 different pairs. And with the square kilometer array, the estimates are that the SKA could find hundreds of new millisecond pulsars, if not thousands. And from those, if you really want to use them fully to search for gravitational waves in their cross correlations, you would get tens of thousands of pairs. So if you really want to deal with all of this and make even forecasts with your full Monte Carlo machinery, is going to get very computationally demanding. So we need some kind of simple, however robust, tools to be able to make forecasts, and also hopefully to be able to guide and optimize data analysis. So people who are working on the CMB field, you know that every time one tries to conceive a new instrument, there's a heavy use of Fisher analysis to figure out how to optimize the instrument and what the instrument might be able to measure, et cetera, et cetera. So now let me get into a little bit more in the thick of it. So I want to first draw some analogies and some differences between electromagnetic waves and gravitational waves. So the number one major difference is that whenever we think of astrophysical sources of electromagnetic waves, they are always coming from an extremely large astronomical number of incoherent microscopic emitters, atoms, molecules. Okay? Even if you talk about a point source, a single source in astrophysics and electromagnetic waves, it is many, many atoms or molecules. And as a consequence, astrophysical sources, astrophysical electromagnetic waves are always stochastic. The electromagnetic field that you measure is stochastic. And all you care about is its power spectrum, i.e. the intensity. For gravitational waves, however, what LIGO has detected, for example, would be the equivalent of the electric field of a single giant gravitational atom. Okay, so for gravitational waves, you can detect what is called, the jargon is continuous waves from single sources, but the single source here is really would be the equivalent of an atom if it wasn't quantized.
Hey, Yacine, can I interrupt for a sec?
Yeah, sure. Wow, it's like a god is talking to me.
Well, that's not inappropriate. Are masers, are there exceptions in the EM sector, like masers and maybe certain kinds of pulsar emission in some frequencies? I'm interested in this because it would be very interesting if because I know what argument you're about to make, and it would be very interesting if we could use that kind of scaling in some E&M context?
That's a good question. I think masers would still be stochastic in the sense that you don't the electric field is not like oscillating all in phase. It's all the same exact frequency, but I don't think the electric field of all the atoms is like exactly oscillating in phase.
I mean, if it's stimulated emission, I think it is, but maybe maybe it's just such a large macroscopic object that in reality it isn't. Oh yeah, you're
Okay.
coming into the chat saying
I have
that
to
the
think about
line
it.
is too wide.
Because I can think of stimulated emission in a purely classical way by thinking of the intensity of the electromagnetic radiation. I don't even have to talk about the electric field. So yeah. I'm not sure, but that's a good question.
Anyway, it'd be cool if there are any counterexamples, because certainly like radio, you can have E&M, right? That's how radios work. You can have coherent
yes.
sources, but yeah. Maybe God doesn't provide.
Well, yeah, I'm not sure. Let's think about it more. So with this exception of masers, to think about some more, all astrophysical sources are stochastic. Gravitational wave sources like LIGO detection is continuous waves, but in addition, you can also look for a stochastic gravitational wave background if you have the superposition of many sources, many binaries, et cetera, et cetera. And this is what I will be talking about, focusing on in this talk. So the electromagnetic waves, the fundamental quantity is the electromagnetic field, say the electric field at a given frequency. So this is a three-dimensional vector, but it is transverse to the direction of propagation, so you have two independent degrees of freedom. The gravitational waves, the fundamental quantity is the gravitational wave strain, which is a symmetric trace-free tensor. And it's also transverse to the direction of propagation. And as a consequence, you also have two independent degrees of freedom in both cases. So this is a very strong analogy also between the two. Now moving on to the description of a stochastic background. So for electromagnetic waves, again, what I was talking about, the intensity here. So if I have two electric fields and I cross-correlate them, so for the experts here, forgive me, I'm not going to have all the Dirac function of frequencies. Okay. So if I take the covariance of EI and EJ, there's going to be one piece here. So there's going to be then 2 times 2, 4 independent components. There's a scalar piece, which is the intensity, a pseudo-scalar piece, which is the circular polarization, and I have 2 remaining degrees of freedom in this linear polarization tensor, which is trace-free and transverse to omega. And if you impose that this contains all of the trace and that it is transverse to omega, there's one single possible geometric form of this tensor that goes here. Okay, this is the identity tensor orthogonal to the direction of propagation. So again, this is the linear polarization, it has 2 degrees of freedom, intensity, circular, linear polarization. Okay, I have 2 independent components again in each one of those 2 guys. So I should have, again, 4 independent components in this rank 4 tensor. So similarly, there's going to be a total intensity, which depends on frequency and in direction, but it's a scalar. And here, this tensor must have all of the symmetry properties and must be built off only out of Kronecker deltas. And so basically, this is going to be the generalization of this object here. And in fact, it's going to be built off products of this object. Okay? And you can exactly derive what it looks like. Then you're going to have a circular polarization pseudo-scalar, and this tensor is going to be some Leibniz-Civita symbols times omegas times a bunch of these things. And the remainder is a rank 4 tensor. It has 4 indices, but it has only 2 independent degrees of freedom. And this is the linear polarization of the gravitational waves. And because it's a rank 4 tensor, it has a helicity 4. And so this is why I was drawing these crosses. It would be the same if you rotate the coordinates by 90 degrees. So I will be focusing in this talk, and in the papers we focus on this intensity part, but all of the formalism we develop could be applied to these polarization parts. Okay, but that's that's a little bit too futuristic for now. We're going to focus on the total intensity. So, and we'll get back to this and why this is useful. It seems like just a purely formal thing, but it's actually very useful. Okay, let's talk about pulsar timing basics. This is a hydrodynamical simulation of a spinning neutron star, which has, magnetic field axis misaligned with the rotation axis. If the Earth happens to be aligned with one of the beams, what you see as a function of time is some spikes in radio intensity. Of course, the spikes don't look as really nice as what I've plotting here. They may have some different shapes, but the point is that they are going to be very regular. So then what do you do? As a function of pulse number, you find the arrival time of each one of those pulses, say the peak of the spike or whatever. You fit some smooth timing model to these arrival times, meaning that you account for the fact that your pulsar may be slowly spinning down. Perhaps it's part of a binary, and so then it has some acceleration and sort of some periodic motion, etc. So you subtract out any deterministic model, and you subtract the black data points from the red, and you're left with what is called the timing residual. So this has units of time as a function of time. Okay, just to give you some real-life example, this J whatever pulsar here, one of the 45 pulsars that were used in nanograph. This is as a function of time, so over a period of almost 15 years, these residuals, which are typically of order of microseconds, okay? And they are measured at different radio frequencies. So you have this function, this time as a function of time residual, and you Fourier transform it. And we're going to work with this Fourier transform, the timing residual Fourier transform. So what are the main sources of timing residual? I'm going to talk about other sources in the conclusions. So first of all, there is the intrinsic pulsar noise and also instrumental noise. So this could have an arbitrary frequency dependence. So here I'm defining the power spectrum. So if I have the timing residual of one pulsar times the timing residual of another pulsar, this intrinsic noise is everything that only depends on a single pulsar, that has no cross-correlation between different pairs of pulsars. How it depends on frequency? One should be completely agnostic, and this is in fact my main criticism of the nanograph analysis, is that they're not sufficiently agnostic about this. And then there is the signal we're after is timing residual, which is induced by gravitational waves. And this looks like this in Fourier domain. So this again has, forgetting about the Fourier conventions, this has dimensions of time. This is dimensionless. So you divide by a frequency. This has two indices. You just dot it into the direction of the pulsar on the sky, and you have some geometric factors, and you get your timing residual in Fourier space. Okay, so now what we do, we're going to take the cross power spectrum, timing residual at pulsar P, pulsar Q. This is going to be some function of frequency, which depends on this pair of pulsar. How is it going to look like? It turns out, if you assume a scalar gravitational wave, if you assume a pure intensity, no polarization, is going to be some integral over all directions in the sky of this gravitational wave background intensity times basically some linear response function, which depends on the positions of the two pulsars and on omega. If you remember how I defined this intensity, you can convince yourself that this is going to look like this dot product with this geometric tensor. Okay. Now, this actually gives you some explicit expression in terms of dot products of the angles of the pulsars and the direction of gravitational wave background on the sky. So this we call this the pairwise timing response function. So if you were to read the PTA literature, you're not going to find this, because what they do is they actually use H plus, H cross, some specific but unspecified reference frame to do their calculations. Here we're doing all the calculations in a purely geometric way, and actually it makes things a lot simpler once you pass the first hurdle of defining things geometrically. So that's one of the first things we do. I don't know if people are going to use it, but so these are these pairwise timing response functions, which tell you as a function of the direction of gravitational wave, how does a pulsar pair PQ respond in terms of the timing residual. So this is just showing these maps. Every function of omega, I'm going to call it a map. As you change the separation of the pulsars, how the response changes on the sky. Okay, so we have this expression, this linear response between the intensity and the timing of the power spectrum. Just as a specific example, which is what has been mostly looked at in the literature, if you have an isotropic gravitational wave background, so it doesn't depend on omega, you can pull out the intensity from here. Then you have this integral over angles of this pairwise timing response function, and this is a function of only p dot q. This has been calculated by Hellings and Downs in 1983. Okay, it looks like this is some function of the separation between two pulsars. So if you have an isotropic gravitational wave background, the same intensity across all the sky, the response of a pair of pulsars will still depend on how far they are separated. Okay, even though you're responding to an isotropic background. Okay, let's now build this Fisher matrix. So the first step is to estimate the noise of your instrument. So take every pulsar separately and estimate its total auto power spectrum, the timing residual auto power spectrum, and I'm going to call this sigma p squared of f. This has units of time squared per unit frequency, but let's just say time squared. This contains everything, okay, whatever there is, because I cannot take a pulsar in my lab and isolate it. So this contains everything that the pulsar makes the pulsar noisy, intrinsic, gravitational wave background, whatever. Then we're going to construct quadratic estimators for the cross power spectra of timing residuals of pulsar P and pulsar Q. I'm going to put a little hat on them to denote them as estimators, and this is equivalent for the CMB to constructing an estimator for the CL by just summing over ALM squared. Okay? So in practice, you cannot make estimators for a single frequency. You're going to estimate them over some finite frequency band. So you make some band power estimator over some bandwidth delta F. And if your bands are wider than the inverse of the total observation time, your different bands will be roughly uncorrelated, frequency by frequency uncorrelated. Okay, so this is the equivalent, if you're familiar with it, with the radiometer equation. So these estimators, we can then construct the n pair times n pair covariance matrix of our timing residual cross power spectra estimators. So what goes in here? So first of all, these are the noises of the individual pulsars. This is equivalent to your detector noise in, say, a CMB analysis, the whatever microkelvin squared for your detector. This, what goes here, is basically the number of independent samples, T times your bandwidth. This is the equivalent of your 2L plus 1 for the variance of your CL estimator. And what goes here is what is called the transmission function. So basically, this accounts for the fact that you are fitting a smooth function to the timing residuals before subtracting it. And as a consequence, you are removing some information at low frequencies. It's basically a high-pass filter. And this, if you want to keep on the analogy with the CMB Fisher analysis, this would be accounting for the angular resolution of your instrument. You don't have information for arbitrary small angular scales, and here you don't have resolution for arbitrarily large frequency, for arbitrarily small frequencies, okay, or large periods.
No, I think the analogy is actually not the window. The analogy actually isn't the window function, but because you're filtering out long wavelength modes. We have the same transmission correction when we do ground-based observing the CMB, because we have to filter out the atmosphere. And
okay.
It really is the same kind of thing. You fit a model to the slow variations in the atmosphere, and then compute a transmission function.
Okay, so that's a better analogy.
Should there also be a high frequency cutoff though as well? Or the point doesn't count Nyquist speed?
Yeah, there would be Nyquist, but it's so much so like it's like every couple of weeks or so that you have these timing residuals, so it's much much higher frequency. But yeah, there should be some Nyquist frequency. So the typical features here is that you have some cutoff at frequencies which are less than 1 over 10 years or whatever the observation time, and then you have big losses at 1 over a year, 2 over a year, because you have to measure the position of the pulsar on the sky, and there's some degeneracies with the motion of the Earth around the sun. So I'm just going to define these characteristic noise strains, just to have things in terms of dimensionless. So this is the timing noise of a given pulsar over the transmission function, and to make it into something dimensionless, you multiply by frequency squared. And this is just to give you an example. This can be computed. This is extracted with the code Hassasiyya that was written by Jeff Hasboon. And so once you analyze each single pulsar in autocorrelation and you estimate its noise, then you can estimate the transmission function and estimate these noise curves. Okay.
Yeah, so you need to be
yeah.
semantic here, but you said it was time squared per frequency, and I always get confused about this. Is this really an object you're going to integrate over a bandpass? And if so, then
so I'm being loose with my units here. So this should be a time squared per frequency, and this should be dimensionless per frequency, really. Or if it's or I can make them both per log frequency. I'm being a little bit loose.
Okay, I'll believe
so
you.
So the characteristic strain really should be dimensional. So there should be another f, basically. I should really multiply by f if I want this to be time squared per frequency.
You called it sigma squared of ln f. And you could have worked in ln f in principle, right?
Exactly, yeah. That's why I'm being loose here, but in the paper it's done correctly.
Fine.
So now what we're going to do is, this is where we take the theorist approximation. Just like one can do a Fisher analysis for the CMB by saying, okay, my CLs, my estimator, so the ALMs for the CMB are Gaussian. I'm going to build some estimators for their power spectrum. They're non-Gaussian, but I'm going to approximate them as being Gaussian. If I have enough independent pieces of information, this is going to be true. Same thing here. I'm going to approximate my estimators for the cross correlations to be Gaussian. And so because I already have their covariance, I can write down explicitly their probability distribution. It's I know the n pair by n pair covariance matrix. Now, because those are linearly related to the gravitational wave background intensity, then if they are Gaussian distributed, then so will be the gravitational wave background intensity. So here I'm going to use a notation throughout that this dot product. So any function of the direction of gravitational wave on the sky, I'm going to call it a map, and any integral over omega of two functions, it's a dot product of maps, okay, for short. So I have this linear relation, and as a consequence, this intensity will be Gaussian distributed. Before writing the full Gaussian distribution, you could write it in terms of the full glory of frequency and angular dependence, but here we're going to specialize to the case where I can factorize the frequency dependence and say some power law, and then the angular dependence of the gravitational wave background. And again, we could do it in more general. So the idea here is that we're going to write the likelihood or the probability distribution of this gravitational wave background amplitude, which has dimensions of strain squared, given the data, which is going to be some Gaussian. And this F here is this Fisher matrix. This Fisher matrix takes this form. It's a sum over all different pulsar pairs. Here you recognize these pairwise timing response functions. And so the advantage of our fully geometric description here is that I don't have to change my basis every time I go to a different pair. And I know exactly how these functions are written. And this coefficient here is basically an inverse variance weighted of the frequency dependence squared of my gravitational wave background. Okay? So basically, to summarize, this Fisher matrix is the noise and geometric properties of the pulsar timing array. This is just the geometric properties, and this is the noise properties. And this is the most compact summary of the noise, angular and noise response of your pulsar timing array. And again, one could make it more general by really having it as a function of arbitrary frequency dependence. So as a first warm-up and kind of neat little results here, if we consider a pulsar timing array with a large number of identical pulsars, distributed isotropically on the sky. Then this Fisher matrix will just be proportional to the sum. The coefficient FPQ is the same for all of them, so I can take it out. So I have a sum of these response functions at omega and omega prime. In the limit of a large number of pulsars, this will turn, you can replace the sum by an integral, a double integral, and this will turn into a function of the dot product between two directions of gravitational wave background in the sky. And this was the hardest calculation I've done in terms of analytic calculations. It involved like rank 4 tensors and 4D integrals. It was horrible, but you can actually get an analytic expression for this function. You can, if you want, you can read it in the appendix. You'll be the only person to have read it probably. So just to check, this is this function. Here, if we have this is 10, you don't see it here, but if you have 10 pulsars, so the Fisher matrix does not depend on just the dot products of two directions in the sky, if you have a finite number of pulsars. This is why if I was plotting it as a function of the angle between two directions in the sky, it is not a function, it's just a scatter. But as I increase my number of pulsars, you see that the scatter decreases and also that the function converges to this analytic expression. So analytic works. So another cool aspect here is that if you have this function which is a function of the angle only, then you can do a Legendre polynomial decomposition. In other words, you can write it as a sum over spherical harmonics, sum over LMs of some coefficient f, which you can compute, it's just the Legendre transform of this function, times spherical harmonic at omega, spherical harmonic at omega prime. In other words, we have written found a basis of orthonormal functions which diagonalize this Fisher matrix. Okay, so the spherical harmonics are actually the eigenfunctions or the eigenmaps of this Fisher matrix, in angle space. So these are the coefficients. Actually, it turns out that the monopole has the largest amplitude, i.e. the lowest noise. So F is the inverse covariance. But then the next one is the quadrupole, and the dipole comes only third, and then the order is preserved. So this is, you can actually diagonalize this Fisher matrix numerically and find what are its eigenmaps. I'm showing here the first 5 eigenmaps for 10 pulsars, 30 pulsars, and 90 pulsars. And what you see is that this becomes more and more like a monopole, and then those become more and more like quadrupoles, as we expect, because the highest eigenvalues are quadrupoles. And if you go on, you would find dipoles, etc. Then another neat thing is something that should remind you of quantum mechanics. So here I'm showing, again, this infinite pulsar limit here in black, and here because you have these, 2l+1 spherical harmonics for each L, so you have degenerate eigenvalues of the Fisher matrix. So you have these blocks, L equals 0, 5 for L equal 2, 1 and 3 were almost degenerate, 4, 5, 6. And as you decrease the number of pulsars, you make this true Fisher matrix deviate farther away from this idealized one. And this is just like perturbation theory in quantum mechanics. It's exactly the same mathematics. It's like you have some Hermitian matrix, which you perturb to find its perturbed eigenvalues, and you see that you change the eigenvalues, and you also slowly lift the degeneracies between these eigenvalues, just like if you had an electric field which would lift the degeneracy in the eigenvalue, the eigenfunction of hydrogen.
Expansions in 1 over n.
This is exactly an expansion in 1 over n. Yeah. And in fact, you can see it sharply here in the convergence. Here I'm showing the difference, and it really scales. I've divided every time the axis by n, it really scales as 1 over n. So this is mostly a toy example to make sure that our overall numerical machinery works. And it's good to compare to something that we know the answer for. So now we're going to apply things to a real data, so to a real pulsar time array, and we use the European pulsar timing array data, which consists of 42 pulsars, which were timed for up to 17 years. This is just showing you how they're distributed on the sky, where this represents, where this is the Milky Way in radio emission. I chose this map because this is also the frequency at which these pulsars are measured in 1.4 gigahertz. So again, the first step is to obtain the typical noise autopower spectra of these pulsars. So this does require some data analysis. You don't get things for free, but you don't have to do a cross-correlation analysis. So it's like if you have an interferometer, you don't have to characterize the noise of your system, you just have to characterize the noise of each antenna. Okay? And then you have characterized the noise of your system. So you have to analyze each pulsar separately, n of them, but not n square of them, not n square correlation, to estimate these characteristic noise trains. Okay? So first thing that we can do for a warm-up is estimate the sensitivity to a monopole and compare it with existing limits. So the signal-to-noise ratio squared, this is kind of like the chi-squared, is the gravitational wave background dotted onto the Fisher matrix on both sides. Again, this has dimensions of characteristics trains squared. And if you have, so this gives you this sum over pairs, this coefficient times this gamma dot A squared. So if we have a pure monopole, this is going to be this characteristic strain squared, independent of direction on the sky. So my signal-to-noise ratio will just be, so this gamma PQ is this A squared times this Hellings and Downs function, which I was mentioning, which only depends on the angle between two pulsars. So your signal-to-noise ratio squared is going to be AGW to the fourth times the sum. And this sum, we know everything about it. This depends just on the this characteristic noise trains of the pulsars, and this just depends on where the pulsars are on the sky. So we can compute the sum, and we can solve for what is the, say, 2 sigma minimum amplitude, minimum amplitude that you would require for a 2 sigma detection. Okay, so such that the SNR would be equal to 2. So we do this not for the full EPTA, because it was never, I mean, we also do it for the full EPTA, but we compare with this limited set of 6 pulsars, because this is actually, with the EPTA, only 6 pulsars were used, using all the cross correlations, because it's numerically consuming. So what we find is that the sensitivity would be 3.4 times 10 minus 15. And for reference, the upper limits that were derived by the EPTA collaboration with the same 6 pulsars were 3.0 and 3.9 10 minus 15 with different assumptions. I'm not sure it's about the ephemeris, but some different assumptions. So we're pretty much in the middle. Now, these 6 pulsars here, why did they choose them? Because they were found to be the best pulsars for continuous wave searches. Okay? So now what we find is if we use the full EPTA array, that you would get a sensitivity to 2.5 10 minus 15, which is significantly better than with the 6 pulsars. So what we can do already with this simple Fisher analysis, if you rewrite this SNR squared as this overall amplitude to the fourth times a sum over pairs, this is the contribution of a single pair to the SNR squared. Okay, so you can rank different pairs by their contribution to the SNR squared. And the key here is that one shouldn't think of individual pulsars, which one is the best, but individual pairs. It's really in pairs that pulsars can measure the gravitational wave background through cross correlations. And so here we can rank all of these pairs, and we find the 44 pairs out of a total of 861 that would give you already 90% of the SNR squared. Okay, so this is already one way that we could guide the real data analysis. One could only focus on these 44 pairs and save up a lot of computational time rather than using all of the 861 that would not give you much more gain in the sensitivity.
Yacine, is the dominant contribution to that the angle between the 2 pulsars, or is it the noise of each individual?
It's really, I don't know, I don't know it's really the combination of both, so I can't really tell you if one is dominant over the other.
I mean, there's certain angles at which the There's
Yeah,
certain
this.
which a pair doesn't help you at all, right? Certain
That's
angles
right.
pairs
Yeah.
don't help you at all. So
Yeah. So there's some angles where this goes to 0, and some of them could be, have individually very good noise, but then the pair could be separated in this weird angle. So it's really the combination of both. I cannot really tell you which one is most important. But the point is that it's easy to compute without, it's very simple to compute.
Those variances scatter plotted against angles.
Sorry, say this again?
You could scatter plot these variance contributions against angles.
You could do this, but the point is that it's so simple to calculate is that you can just, you could just calculate it and that's it.
Yeah, although if you wanted to guide like searching for more pulsars, if angle matters, you want to search in particular places. Right.
So this we did initially an analysis of this thing. If you wanted to optimize this and you were to add one more pulsar, where would be the best place to put it? And the answer is quite simple: is that you would put it the closest possible to the least noisy pulsar, because this is the Hallington-Downs correlation is maximal at 0 separation. But because this SNR typically scales as the number of pairs, even if, let's say, only 44 pairs contribute, if you really think about adding one pulsar at a time, it would contribute so little to your SNR squared that you can only think of the improvement of adding many pulsars at a time as something meaningful. And then, you can't really focus on searching in one area or another because, they're going to be themselves correlated with one another. And so, yeah, we thought about this question, and in the end, we convinced ourselves that it's not really, you wouldn't be able to guide where to search for new pulsars.
Understood.
Like if you use SKA, if they find 100 new pulsars, well, they're completely going to blow out of the water the existing ones. Like they're not going to try and focus on where they are. Should I continue, David? We can also talk, I guess later, David, you're probably like just around the corner or something.
Yeah, I'm several feet away from you, but in
so funny. So, okay, let me move on because I don't know how much time I have left. So let's go beyond the monopole and talk about anisotropies. Okay, I'm gonna get some water actually. Can I like drink from the fountain, or I'm just gonna get?
Keep it up and we'll bring you water.
Oh, thank you. Yes, I have to put my mask on too. Okay. Beyond the monopole. So one point I want to make, which will seem obvious when I say it, but it hasn't been obvious in previous publications. If you have n pairs of pulsars, you can only measure, and if you assume some frequency dependence, you can only measure n pair independent pieces of information. That seems like a trivial statement. So what does it mean in terms of the gravitational wave background? So if I have a gravitational wave background map, thank you very much. So if I have a gravitational wave background map, I can think of this as, maps are an infinite dimensional space. Okay, so I can only measure n pair components out of this infinite dimensional space. So basically there is a space, which is n pair dimensional, of observable maps, and then there is an infinite minus n pair dimensional space of completely invisible maps to the pulsar timing array. Okay, so we can understand now, because there were some limits on anisotropies by the EPTA collaboration, and what they produced is these upper limit maps on every single one of 12,288 pixels. And so using only these 6 pulsars, which are 15 pairs. So already this is something cannot be possible. How can you simultaneously constrain more pixels than pairs? And so we figured out what this was, and basically what they were doing, because they were using this Moore Penrose pseudo inverses in their analysis. So they were actually constraining the amplitude of the observable component only. But that doesn't, so this map cannot be interpreted as an upper limit on the actual gravitational wave background, because for a given observable component, you can have an arbitrarily large invisible component, okay? And just to show that we actually really understand what we're doing, we were able to make a forecast of this map with our Fisher formalism. So the qualitative features look strikingly similar. We're off in amplitude by a small factor, but we were also off in amplitude for the monopole because, of course, this is not the exact data analysis. But the features are similar, and also this is with the actual realization of noisy data, and ours is just some forecast. So we don't expect them to be exactly the same. So again, those are not upper limit maps. And to drive the point further, if we did the same analysis, not with 6 but only 2 pulsars, then you would actually get these maps with a lower amplitude. Okay, so if you add more data, you should have better constraints, but here is the opposite which is going on. Why? Because if you have only 2 pulsars, the set of observable maps is actually one single map, is actually spanned by the pairwise timing response function of that one single pair. And so, whereas here you have 15 dimensional space, and in this 15-dimensional space, some of the maps have very large noise. Okay, so again, this is just to drive the point that these are not actual upper limit maps, and you cannot make an upper limit. You cannot constrain more than n pair coefficients simultaneously. So how can one go about and use this Fisher matrix to make forecasts for anisotropies? So suppose that you have some good physical reason to expect that your gravitational wave background should be some linear combination of some known basis maps. Okay? And you want to estimate how sensitive your PTA is to each one of these amplitudes. So first of all, again, got to take a break, stop. If you have more than n pair maps, this is bound to fail. So you can only do this if you have at most n pair maps. So given that this is Gaussian distributed in our approximation, then these coefficients will also be Gaussian distributed. And their covariance is the inverse of this discrete Fisher matrix obtained by dotting these basis maps onto our Fisher matrix on both sides. And so given this covariance, you can compute the 2 sigma sensitivity by taking 2 times square root of this variance. So this is what we do in multiple examples. So the first example as a very simplistic example, the simplest you can think of if you want to go beyond the monopole. Say I have a monopole and a hotspot. Hotspot in the gravitational wave background. So I emphasize that, so this is a Dirac function, you can call it a point source, but remember that this is still stochastic gravitational wave background, so you would have to have a very large number of actual sources in this hotspot. So this is showing as a function of the assumed to be known direction of the hotspot on the sky, the sensitivity to the monopole, and to this hotspot coefficient. So for example, so this would be the sensitivity if you had no hotspot at all, it would go to 2.5 times 10 minus 15. So in these regions, you would be able to measure the monopole and the hotspot amplitude rather well simultaneously. But in this region, you would still measure the monopole rather well, but not the hotspot very well, et cetera, et cetera. So this is just obtained by computing a 2x2 Fisher matrix for these 2 coefficients and then finding its covariance. And again, you need to have a previous knowledge of where the hotspot is, otherwise you would have an infinite number of parameters. Second example, if you want to set an upper limit as a function of directions on the sky, you can only work with coarse pixels. And the main point I want to convey here is first that your overall sensitivity, so this is sensitivity after marginalizing over all the other pixels, gets significantly worse as you increase the number of pixels. And also, if you ask what is the sensitivity to the monopole, the average of all the pixels, it decreases. You cannot just take the average of these maps, but the sensitivity decreases significantly as you increase your number of basis functions. Same exercise with spherical harmonic amplitudes. As you increase your cutoff, you say that I have a sum over spherical harmonics up to some L max. As you increase the L max, the sensitivity to any one of the coefficients degrades. Okay? So the bottom line is that the sensitivity to each coefficient is going to systematically degrade as you increase your space of maps. And why is that? It's because the standard maps that we use, the standard bases that we use, pixels or spherical harmonics, they are statistically correlated. They're not independent. They have covariances in terms of the response of the pulsar timing array. So you better have a really good physical reason to say that I have no signal whatsoever beyond Lmax of 10. Otherwise, this is an exercise that is doomed to fail because, as you crank up, you cannot constrain all of, arbitrarily large Lmax. So what's one possible solution? And I should get done soon. If you are completely agnostic about the gravitational wave background angular dependence, then you want to search under the lamppost of pulsar timing array. And what is the lamppost? Is asking what are the principal maps, the most detectable maps of the pulsar timing array. And those are the eigenmaps of the Fisher matrix. So those are n-pair orthogonal and statistically independent maps, which span the space of observable maps. And so you can search simultaneously for the amplitudes without degrading the amplitude of, say, the first principal map if you account for more maps in your analysis. So this is the better defined set. So this is just to show you that these principal maps do not look at all like spherical harmonics. There's no reason why they should for a real pulsar timing array. And to show you here how their sensitivity increases with map index. So I want to go through this. I will take 3 minutes. I'm sorry. I will take the 3 minutes. This is kind of cool.
I'll give you 3 minutes.
Okay, thanks. So we can use these principal maps as a basis to try and reconstruct agnostically the gravitational wave background. So what's the idea? It's similar to what one does in interferometry. Search for all of these amplitudes of these principal maps. Okay, then you can say, okay, each one of them I know whether I detected it with what signal to noise ratio. And I can define my reconstructed map as the sum of these best fit amplitudes times the principal map. But I only can keep the maps whose amplitude I measure with SNR greater than 3. This is what you do when you do a dirty map in interferometry. You can only measure a finite number of Fourier modes on the sky, and you say, when you plot a map like the EHT or whatever, what you're really doing is discarding all of the modes. You're setting them to 0, all the modes that you don't measure. So here we're doing the same thing. So this is just to show you an illustration. I'm going to put these two input maps, which have the same monopole. This is my prediction of the gravitational wave background. It is tautologically true. And here I'm going to show you the reconstructed maps as I crank up the amplitude with the current EPTA noise parameters. So if I crank up the amplitude of the monopole to 10⁻14, which is already would be measured by a signal-to-noise ratio of 30, okay, what you would measure is only 3 principal maps in both cases. And this is your reconstructed map. If you crank up the amplitude by another factor square root of 3, you would measure 9 and 13 principal maps. This is now a signal-to-noise ratio of 100. Of course, it's already ruled out, but this is what you would need, and still cannot really say much. And if you crank it up again, signal-to-noise ratio of 30 would be for the monopole. You would sort of start to see the G here. So my conclusion is that PTAs for now are not quite at the level of detecting anisotropies. But why? As long as you haven't detected even one single number, it is, of course, wishful thinking to think that you might be able to detect more than one. Okay, so it makes sense that for now, PTAs cannot detect anisotropies. And the issue is that contrary to interferometry, the noise of principal maps is not the same everywhere. So in interferometry, once you detect one visibility with a good SNR, you detect all of them because they all have the same noise. Okay, so the conclusions. First conclusion in terms of anisotropies. An important yet obvious point, or obvious yet important point, which is that you can only simultaneously constrain n-pair independent components. If you search for a monopole plus spherical harmonics or pixels, as you make your basis function bigger, you're going to degrade your sensitivity because of the correlations between these functions. You can search agnostically for anisotropies by using this principal map basis. But first of all, they're not actually, I didn't talk about this, but they're not, the monopole is not a principal map, so you don't really search for anisotropies. You're going to search for different maps, but they're not pure anisotropies. And still, you would require, with current PTAs, you would require a very large signal to be able to even distinguish obviously different maps. Okay. So the prospects right now for detecting unknown gravitational wave background anisotropies with current PTAs are very limited, but again, because we haven't detected anything, it makes sense. But I think what might be interesting is to search for anisotropies statistically rather than specific form. And this is my last slide. So future extensions. In terms of the noise, one can include more realistic sources of correlated noise. This would be the equivalent of CMB foregrounds. For example, a global clock error, which leads to a fully correlated timing residual independent of the pulsars. You have to compare your times of arrival to a global clock, or some errors in the solar system ephemeris, which would lead something that looks like a dipole. So the equivalent of knowing the frequency dependence of CMB foregrounds here would be knowing the angular dependence of these sources of correlated noise. One could try and go beyond the weak signal limit. And in general, the goal would be to build some as robust as possible forecasting tool to not have to use, Monte Carlo simulations if we want to say what, say, SKA pulsars would be able to see, et cetera, et cetera. I'll stop here. Hopefully, I'm 2 minutes beyond the time. Hopefully, you'll forgive me.
All right, let's thank you. So we have time for a couple of questions. There were several during the talk, but if you'd like to ask one, raise your hand on Zoom. So let's start with Yuri.
Hi, Yacine. I was wondering if your Fisher estimator depended on the fact that the signal, say the stochastic gravitational wave background, is significantly smaller than the noise in each individual pulsar.
Yeah, that's exactly what the weak signal limit is. Yeah.
Okay, and then I don't quite understand your assumption about Gaussianity, because it seems to me that the square of the Gaussian noise is not Gaussian noise.
You're right. It's not Gaussian, but just like it's the case for like the CLs and the estimators for the CLs. But if you build your estimator out of a sufficient number of independent samples of data, so to be explicit, if you have a bandwidth delta F which is large compared to your inverse observational time, then you can make the approximation that you have a large number of independent samples of the same thing, and then it will be approximately Gaussian. But yes, it's just an approximation. Right? It's not, and it's an approximation that will be more accurate when you go to higher frequencies, when you can afford to have a larger bandwidth. But yeah, it's not perfect. But I would also argue that in the current PTA data analysis, the assumption is that the time of arrivals are Gaussian distributed, and I don't know if it's
that's probably a much better assumption than that the square of the times of arrival.
Yeah, but why? What's the fundamental reason behind it? I don't know. I mean, yeah, I'm not sure what's the fundamental reason behind it. But I agree that it's this is a theorist analysis, and so it's a simplification for sure.
Hog?
And Yacine and others have heard me ask this question before, and feel free to punt it. But in these pulsar timing arrays, you always treat the pulsars as just being a statement about the timing noise for the Earth, but the pulsars themselves are also in the stochastic gravitational wave background. And so in principle, there's correlations between the pulsars that depend on their three-dimensional positions. If magically you could know the positions of the pulsars, the distances of the pulsars very accurately, would you be able to use it to improve the stochastic background measurement? I have an intuition that says you should be able to do far better. But
I know we bet what, a couple of bottles of champagne or something a while ago.
So have you thought any more about that question?
So I think that even if you knew the distances perfectly well, the issue is that, so if your gravitational wave background has only large angular scale fluctuations, this pulsar term that you're talking about, effective because it has a high, it's like an e to the I, theta times some very large thing. So basically you're multiplying, you're integrating your smooth gravitational wave background times a very rapidly oscillating function. Even if you knew exactly the frequency of oscillation, you would still have a suppression if your background was smooth. So I don't think it's so much an issue about not knowing, it's just like this term is extremely small because it's a rapid oscillation.
Because the stochastic background is so broadband that it decoheres rapidly.
Yeah, but if you had like a very high L, like a very small scale angular scale variation in the stochastic background, then maybe you would get something. But
the funny thing about that is that the background is made up of a number of sources that are, if you only have measuring it at one point, it's true that it decoheres fast. But if you're measuring it at multiple points in space, if it's being generated by a small number of individual sources, like even
then you have to think, and that's I think it's an interesting question, which I don't know if maybe Yuri would know if anyone has solved it like in a clear way. When does the background become stochastic? When is my mathematical assumption that I have a stochastic background, when is it accurate?
My fundamental intuition is that is different. That limit will be different if you know the pulsar term versus if you don't. Like you know the locations of the pulsar. I mean, another question you could ask, which is kind of similar, is imagine there was an alien civilization that was also doing pulsar timing, and they were telling us what they were learning. So they were beaming to us their pulsar timing data. So we were learning, you're seeing all of their pulsar timing data and all of our own pulsar timing data. Would we only do square root of 2 better?
Oh, you think you could do better than square root of 2 better?
I think we would do way better than square root of 2 better because even though it's stochastic for us and it's stochastic for them, it might not be jointly stochastic.
You should prove it, David, because there's like 2 bottles of champagne in the game.
I know that Chiara posted a relevant paper in the chat on Zoom, so it may already be solved, but I'll let you guys follow up about that. In the interest of time, we should probably wrap up unless there's any final burning questions.
I just wanted to say, Colin, the paper I posted in the chat was on the issue of stochasticity and when is the background stochastic. So this is a Cornish and Romano 2015 paper where I think that's literally the title of the paper.
Yep, great. Thanks, Chiara.